And so when we have cases that involve either of these two, where both alpha carbon and beta carbon are chiral, or they're in the same ring, we need to consider this anticoplanar rule. So let's draw out two practice problems here. I'm going to use a cyclopentane ring, and I'm going to have our leaving group coming out towards us, and then I'm also going to have this methyl group here. Here's a hydrogen. Let's draw in our base. And as we look at this, and I should write that this is racemic, we're going to have both enantiomers here in our reaction flask. And the product that we get from this is definitely an alkene, okay? And it's going to be the most substituted alkene. It's going to be the following. Now here was our alpha carbon, and here's our beta carbon. This used to be the alpha, and this used to be the beta. When we're looking at this, yes, we made the most substituted alkene, but the key point here is that this hydrogen and this bromine are anticoplanar. When it's in a ring like this, a key thing or something that kind of helps you spot if this can undergo an E2 reaction is that the hydrogen and the bromine need to be on opposite sides, and in this case it's a wedge and a dash, okay? That might help you, and vice versa. So the wedge and dash, let's see, we need, so this is for the leaving group and the beta hydrogen. They need to be opposite. Let's go over an example where we actually don't have that hydrogen there. What if I still had the same stereochemistry here? So there's that hydrogen, but what if our bromine here was going down? And we had a racemic mixture here. Well, we're kind of stuck. My question here is, can I make the most substituted alkene here? Well, in this case, here's our alpha carbon, okay? And we do have two beta carbons. But the beta carbon that's on the top that we used in the previous example doesn't have a proton that's anticoplanar to this bromine. So we can't use that beta carbon. We won't be able to form the most substituted alkene. So instead, we're going to look at this beta carbon. And we're going to notice that, oh, cool, we have two hydrogens here, and we can use the hydrogen that is opposite of this bromine. That was about the weirdest box I drew. Okay, cool. So for this reaction, we're going to get a different major product for this E2 reaction. We didn't touch this chiral center here at the top. That didn't change, but we now have an alkene here at this beta carbon. Notice the difference here in these two reactions, all right? Now, I started with the racemic product, okay, and that means that I also have the other enantiomer. So you will end up getting a product here that is racemic. I can draw through this really quickly to show you. So this whole racemic business, let's practice this. This also means that you have the other enantiomer of your starting material. Both chiral centers will switch. Okay? Our bromine is now coming up, and the proton that's here is now coming up. When we do the E2 reaction, these two are not anticoplanar, so you still have to pick the proton from the less substituted carbon there. But now you're going to have this methyl going back, okay? And this is a chiral center. That means you will have both your R and your S as your product. So on the exam, you can just write this. This is signifying I have the methyl, the product where the methyl is coming forward, and the product where the methyl is coming back. I have both the R and the S for this. All right. Let's look at some 6-membered rings here. Let's look at some cyclohexane chairs. Chair conformations. Woo! All right. We're going to use potassium terbutoxide. Okay. And we can see that we're probably going to do an E2, right? Well, it also says E2, but we have a really bulky, strong base. Bulky, strong base. As we're looking here, we're going to label our alpha and beta carbons. This one has 2 beta carbons. And we're going to first ask, okay, we're pretty sure we're going to do E2. Are there protons on the beta carbons? There are. Second question is, do we have any protons that are anticoplanar or anti-periplanar to our leaving group? Our leaving group is that chlorine there. And so as we're looking, the chlorine here is coming towards us. So we're looking for a proton that is going back, actually. So this one would work, and this one would work. So either of those 2 protons would work. Now my question is, which one is it going to take? Well, we know that the more substituted alkene will form. This is Zaitsev's rule. So actually, you could go ahead and draw the product knowing this. We have a cyclohexane ring. We know we're going to put a double bond on this side of the molecule. We're going to deprotonate our proton here, push the electrons down, and kick out our chlorine. Notice that the double bond is in between those 2 alpha-beta carbons. So this is your product. Now, I want to highlight something here. This methyl here is flat. This is wrong. You can't put a wedge like this. Remember that this carbon here is now sp2 hybridized, which means that it is planar. So you always draw them flat lines when you're dealing with alkenes. Sometimes, just as an aside, sometimes you'll see an alkene that looks like this, and then it's drawn. You might have professors who do this. I'm going to draw this out. This is as if you take the alkene, that this is now flat on the piece of paper, and it's like you've turned it, okay? So then the plane is now going out towards you and behind it. So just pick up a piece of paper, look straight down in it, hold it right under your nose, okay? Now put the piece of paper right in front of you, right in front of your nose. That's essentially what you've done with the alkene. You've just kind of rotated it up 90 degrees if you draw it like that. So a way to avoid drawing it incorrectly is just never draw wedges and dashes on your alkenes, and then you're less likely to make a mistake. Okay, cool. We just did this without drawing a cyclohexane chair, but it's worthwhile for us to figure out how to do this and be able to do the chair flip and understand the relationship between our leaving group and our proton. So here I have a cyclohexane chair. I'm going to go ahead and draw my methyl here. We're going to draw a CH3 coming up, a hydrogen going down, okay? And our chlorine here is going up, and our hydrogen's going down. And then we have one more beta carbon that we could draw in. Cool. This is our cyclohexane chair. Here is our chlorine. It's our leaving group. And we've already decided we're going to be taking this proton. Notice the relationship between our leaving group and our proton here. These are anticoplanar. Now, you can imagine that you could get a structure where it's actually drawn where both groups are not axial. These groups are axial here. They just happen to be axial because of how I drew it. So let's draw the chair flip where they aren't axial anymore. CH3, our proton, okay? And then this side is going to have our leaving group. When we're looking at this, our leaving group is equatorial, and the proton that we're interested in is also equatorial. Now, I can take this one step further and help you see that these are not anticoplanar, all right? So I'm going to do a Newman projection looking down this bond right here in red. So I'm going to draw my Newman projection. My chlorine is going up and to the right is the way I'm going to draw it here. And on this side, this is where we have the rest of the ring. Okay, and then going up on the back carbon there is my CH3. I'll put that in blue. Sorry, this side has the rest of the ring we're attached to. Okay, and then on the right side, this is our hydrogen that we are interested in. Kind of messed up on coloring there. There we go. Okay, leaving group is in red, and then our hydrogen of interest is also in red. Now notice that these are gouged to each other. They're right beside each other. Now, I'm not showing that they're huge steric hindrance here. It's really between the CH3 and the chlorine. But what I'm showing you is that these are not These are not anticoplanar. The only groups on a Newman projection that are anticoplanar are if they're completely opposite of each other. Remember, the anticoplanar means they need to be opposite and have a 180-degree dihedral angle. These two groups do not have a 180-degree dihedral angle. So we wouldn't draw the mechanism on this. So I'm just going to write this out. Leaving group and hydrogen must be on axial positions and opposite of each other. This is really important. So in this example in the top, you actually were able to solve it without drawing the cyclohexane chair. You notice that the hydrogen and the chlorine were opposite. One was dashed and one was wedged. You could draw the product. You know that alkenes are flat, so we're not going to draw any wedges. This is wrong. And if we draw the cyclohexane chair, if you were given this conformation, remember, is just how it is rotated. You would need to rotate it into the one where both are axial. Both leaving group and hydrogen are axial. Of course, I showed you how to solve it without having to draw the ring. Let's do another example together where this whole being able to be axial is really important.
All right, so the video is getting too long, so nice job. You got done with the ring part 1. High five. That's not quite a high five, but that'll work, Rudy. Thank you. We're going to go over terbutyl groups in cyclohexane chairs, and they cause little issues when you do E2 reactions. Coming up.